Greetings, my name is John Gabriel, and this is the New Calculus channel. So today I'm going to discuss the unbearable stupidity of mainstream academics. This is going to be an exciting video, so don't rush off just yet. Let's begin. So, I don't know if I've told you about my article on LinkedIn which describes what it means to be well-defined for any concept. But it was the first article that was ever written, and there were no books or articles written on the topic before I wrote my article. After it had been written, there were many on Wikipedia who updated their entries, changing their articles. They even coerced the editors of Webster to change the tangent entry in the Webster dictionary because I would use the original against them so often. Can you believe that? Yes, they did. And they actually ended up stabbing themselves in the foot because the new definition in Webster's doesn't actually work for all their limit definitions. So it's kind of funny that they went and changed that so that they could make it, they were changing the facts so that it could suit their theory, a very Einsteinian thing to do, and in the process ended up hurting themselves more than they thought. So what I'd like to do is show you a trichotomy of mainstream definitions that don't get past the first and second requirements of what it means to be well-formed. Just very quickly, this is the article. In order to be well-formed, a requirement must be reifiable, either tangibly or intangibly. It must be defined in terms of the attributes which it possesses, not those it lacks. It must not lead to any logical contradictions, and it must exist independently of the human mind or any other mind as a nomenon. This means it must exist in a perfect Platonic form. So, those are really the four requirements. And let's start off with Exhibit A. But before we start off with Exhibit A, notice that the idiots begin most of their concepts in calculus with the ill-formed concept of infinity, which cannot be reified in any way, shape, or form whatsoever. So the infinity concept fails on the very first requirement. That is, it can't be reified either tangibly or intangibly, and writing an ellipsis or three dots doesn't reify infinity in any way whatsoever. So the first exhibit that I'd like to talk about are Dedekind cuts. They're supposed to be unique, but it is easy to show from the definition, okay, that it's ill-formed. So it might get past the first two requirements, but it fails miserably on the third. So, in other words, it leads to logical contradictions. And the one that comes to mind straight away is that no cut is unique. Let's see. Like most of the nonsense in mathematics, Dedekind cuts are defined by everything that they are not. So if you look at this cut here, for the real number k, it supposedly contains all the rational numbers except the one it represents, which is k. And for example, to compare square root 2 and square root 3, we can't use d squared is less than 2 and c cubed is less than 3, and from this generate the lower and upper sets showing that they're different, because then we're using inequalities which approximate the numbers, never the actual numbers themselves. And no number is defined by a formula. A number is the measure of a magnitude. Let's see what this means dynamically in an applet. So these are the rational numbers, say for example this cut here, 1 over square root 2. And as we do this, supposedly this 1 over square root 2 is defined by every rational number except itself. Isn't that ridiculous? Totally ridiculous, isn't it? So no cut is actually unique because it can't be found in a logical way. So this this uniqueness attribute, according to Dedekind cuts, is false. There is no unique Dedekind cut, even though they claim that it is unique. If you take a number very close to this 1 over square root 2, it will still contain most of the same rational numbers in the lower set as it does in the upper set. So this is Exhibit A, okay? And I'm not going to save this. And I've just shown you now that Dedekind cuts are nonsense. The next exhibit is B. The definition of a mythical irrational number is a number that is not rational. In other words, one that can't be represented as the ratio of two integers. But wait a minute. That's all we really know to be a number, the ratio of two integers. In other words, it's the measure of a magnitude, not the partial or approximate measure, but the complete measure. That's what measure means. So we know for certain that the measure of a magnitude results in a rational number. But if it's not a rational number, then what is it? Is it a gorilla, a pencil, a balloon? All of these objects satisfy the definition for a rational number, because none of them can be represented as a ratio of two integers. And I can think of many more objects that satisfy an irrational number. For example, you satisfy an irrational number because you can't be represented as a ratio of two integers. And let's see again dynamically what this means in an applet. So if you look at this applet here, it shows you how to approximate the measure of square root 2 by dividing the sides here into greater granularity. So for example, you start off with 10 and you move on to 100 and 1,000 and so on. And each time you'll see this is the rational number approximation, which is the same as this. Okay, 1.0 is the same as this. So as you approximate it better and better and better, you'll see that you can never actually find a number, P over Q, which represents this incommensurable magnitude, square root 2. Not even God can measure this. Did you get that? You're a bloody moron if you think that a Taylor series can measure it and that even trillions of digits are accurate. They're not. You can take billions of digits, as many as you like, and if you take that as a proportion of the total infinite, the mythical infinite decimal expansion, it's 0. Okay? So it's not accurate. It's never accurate. It doesn't matter how far you go out. Okay? This expansion here is never accurate. Right, so this is Exhibit 2. And I can't tell you how irate it makes me when anybody calls a magnitude that is not commensurable with any other magnitude a number, because a number is the measure of a magnitude. That is the proper definition of number, which I, John Gabriel, tell you it is. Everybody else before me is a fucking idiot. And what I am telling you is correct. Okay. Now you go back to your lecturers and you educate them. You get them to watch these videos and you get them to study what I've been telling you here, because they're producing morons like you. And that's a terrible tragedy. All right. So now let's get back to the, I didn't want to do that. Oops. I didn't want to do that. I want to get back to the PowerPoint. So we saw Exhibit B. Now for the last one, of the trichotomy, let's not forget the bogus definition of the derivative in mainstream calculus. So the derivative is defined by every finite difference in an interval except the one that actually matters, the one at the point of tangency. Okay, that is the one at x when h is equal to 0. But of course, supposedly the limit here doesn't allow it to equal to 0, because the orangutans thought they tried to pull the wool over our eyes and tell us they rigorized it. But they rigorized nothing. And the Weierstrass epsilonic statement is not a definition. It's a verifinition. It verifies the limit, which you can only find by setting h equals to 0, you moron. Okay? You're a moron. Now, I'm trying to change your moron status. Let's see dynamically what this means in an applet. So if we come over here, not this applet, but this one. So these are the finite differences yet. Don't worry about this yet. Just watch the finite differences, okay? See, it's defined by all the finite differences, but you can't, it's not defined at the point of tangency, okay? It's not defined at the point of tangency. The minute you get to the point of tangency, it's 0 over 0. Isn't that ridiculous? Totally ridiculous, right? So, okay, well, I can't get it right on the spot, but anyway, that's what it means. And as you can see, I've shown you 3 examples of the idiocies in mainstream mathematics. Hope you've enjoyed this presentation, and I'm running out of time. I only have 11 minutes for each video. And I hope you'll join me again next time for another exciting episode. I'm John Gabriel, and this is a new Calculus channel. Till next time, goodbye.